I'll also try to check the waiting room. And if I know the names, I'll let them in.
That's okay. Yeah. So I'm joining with my other camera.
Okay,
Just let me in, Chen. So I think
I did.
yeah, okay.
Okay.
Okay. Yeah.
Okay, yeah, we can see it. So I'll get it started. I'm sorry from everyone. Really, it was a bad luck, but we're starting over. Hi, everyone. Welcome to our monthly seminar. Today, we are excited to have Dr. Enze Chen. Dr. Chen is a postdoctoral researcher in the Department of Mechanical Engineering at the University of Wisconsin-Madison. He received his PhD in civil engineering from Johns Hopkins University in 2024. His research sits at the interface of solid mechanics and biology, combining high-rate experiments with multi-physics modeling. He studies how energy from blast waves and directed energy travels through brain tissue and how the resulting deformation drives cellular level responses. He also works on brittle and soft architected materials with applications to the design of tissue engineering scaffolds. His broader goal is to establish predictive mechanics-based frameworks for biological systems that connect external loading to mechanical deformation and resulting biological response, enabling a mechanistic understanding of injury mechanisms and mechanobiology. Please join me in welcoming him. Dr. Chen, the floor is yours.
Yeah, thank you, Oscar. Yeah, so today I would like to I'm not sure how many people are familiar with the blast exposure, but today my talk will be focused on how the blast injure the brain. So for the video that you're looking at here, you could imagine that when these warfighters sit next to the artery, when they fire, the blast from the discharge travel to their brain within few milliseconds, even faster than they can blink. But for decades, we cannot say with confidence what happened does the blast wave do to the brain. So today in this talk, I'm happy to share our new insight on the physical mechanism of how the brain gets deformed under blast exposure. And because it's the first time we'll be able to see it within the brain, so we can tell people here that the mechanism is coming from the head rotation, from the net moment due to the pressure field from the blast exposure. Okay, so before I go into the science, I would like to thank the people who make this work possible, especially the entire Panther program, especially Dr. Tim Bentley, who's our program manager for the Panther, and Dr. Christian Friend, he's a Panther director in UW-Madison here, and he's also my postdoc advisor. Okay, so for the problem we try to solve today, it's primary blast traumatic brain injury. So what you're looking at here is a free body diagram or a diagram for the loading condition from blast exposure. So you see here that we have an instant blast overpressure propagate from the left to the right. And this typically have a Freelander waveform, which has a rapid rise in the overpressure and a positive phase. Together, these carry the impulse or the momentum from the blast exposure. So when the blast wave hit the head, it's going to generate a symmetry pressure loading on the surface. So if we integrate the pressure, we can get the net force from the blast. And if we use the net force times the moment arm of the head, we can get the net moment from the blast. Okay. So the key problem we try to solve here is to understand how does the blast interact with the brain, the head and the brain, and what's the role of net force and net moment in give rising to the internal deformations. Okay, so here's another video that to show you where does this most exposure happen. So you can see a warfighter was firing a motor here, and when you see the motor discharge, there's a strong blast wave propagating and hit his head here. And you can see a significant amount of head motions and rotation here. So for our talk here today, we could be focusing on the BOP level from 4 to 30 psi, which correspond to the tier 1 weapon range. Okay, so what do we know about blast traumatic brain injury? So we know that blast-related traumatic brain injury is a significant health burden for U.S. warfighter and often called as a signature injury from war in Iran and Afghanistan. However, the injury pathology is somewhat inconsistent from what we know from conventional TBI. So what I'm going to show you later is the comparison between the pathology from a blast exposure, which is what we're going to study here, and comparison to the pathology from inertial TBI. So I'm going to show you some pathology from the sweep speedboat rider. So when they're on duty, their head experience significant amount of rotational acceleration and deceleration. So we can compare these two pathology to show you what is consistent and what is inconsistent in the pathology. Okay, so before I go into the pathology, I want to show you guys the anatomy of the brain. So to give you a brief overview of how the brain looks like to better understand the picture I'm going to show later. So in these cross sections of the brain you're looking at here, the outer layer you have the skull, and then you have the brain tissue inside. So here's the gray matter, and you have white matter. Then you have gray white matter interface here, and then in between the skull and the brain tissue, you're gonna see the subarachnoid space, which is the connective tissue for the skull and the brain. Okay, so the picture I'm going to show you now here is a post-mortem staining from Dr. Dan Pro's group. So what they found here, so here you're looking at here is the subarachnoid space I just showed you, very outer layer of the brain, and then you have the gray matter interface. So what you're looking at here is called GFAP staining. So GFAP staining stands for exercise in the brain, which is one type of supporting cell in the brain. So this high intensity here is an indicator of atherosclerosis. So this is an indicator of brain injury, a typical indicator of brain injury. So you can see that in this chronic blast TBI postmortem examination, you see a very clear pathology that's widespread atherosclerosis in the gray-white matter interface and in the subarachnoid space. So in blast exposure, we see widespread injury. Okay, so how about the inertial case, so the conventional TBI? So what you're looking at here, also from Dan Pro's group, so they did a postmortem examinations of the speedboat rider spring. So you can see that. So for this GFAP staining, you see very similar pattern that's very diffuse at the gray-white matter interface. So in this comparison, we can see that the similarity comes from both blast TBI and conventional inertial TBI. They both have diffuse injury. Okay, so this is one similarity. So what about the inconsistent here? So the inconsistent comes from the pathology in CTE. It's chronic traumatic encephalopathy. So you can see that in the study from Dan Pro's group that they examined the CTE case from the military warfighter, and they found that in military blast exposure, it's much lower rate compared to impact TBI. So CTE is lower rate, has lower rate in blast compared to impact TBI. So how about the inertial TBI? So the same study that from Dan Pro's group who showed that, so this is also the brain stain. They show that this is staining for the phosphorylated tau protein. It's a hallmark of CTE. So they do see a high expression of the p-tau in the brain slice, which indicate that there's a sign of CTE in this inertial TBI case. So now we can say that the similarity comes from the diffuse injury, but the differences comes down from one has lower CTE case in the blast and one have higher CTE case in the impact and inertial TBI. And we believe this mechanism comes down to the brain strain and brain strain rate. So I'm going to explain this at the end of my talk. Okay, so what are the current hypotheses to explain the pathology? Okay, first, because people think, okay, if there's an injury in the brain, there must be deformation. So people start to use numerical simulation to understand what's the tissue strain following blast exposure. Okay, so this study that showed that at very high BOP level overpressure from 44 to 73 psi, they only see around 1.2 to 1.5% string. So the string level is very low. So this is hard to explain the pathology because at this string level, we believe it's not injurious. Okay, so then people move to a to the pressure-driven event because blast overpressure is actually a pressure-driven phenomenon here. So what the researcher tried to understand is where there's going to be any inertial cavitation in this case. So this group, Guler's group, that they design a gel phantom which exposes the shaft from the left to the right. So this you're looking at a gel phantom, like a head gel phantom, and then they have the pressure sensor at the back of the head. So it's contra curve. And they try to see if, and they found that when the blast hit the phantom, they saw the cavitation at the back of the head. And they also measure negative pressure inside the phantom. So they think, okay, this could be one of the possible mechanism for the injury. However, can cavitation explain the pathology? No. We believe because the initial cavitation, it's hard to explain the widespread injury because it's stochastic nature. So it could only happen as spot by spot at certain locations, and it requires very high nucleation threshold. So we don't think this can explain the diffuse injury we just saw in the previous slides. Okay, so the bottom line here is that with all the study outside, we still lack of understanding of the physical mechanism that's consistent with the pathology we just saw. Okay, so I want to tell you guys why it's so difficult to pinpoint the mechanism. Okay, first it's because this is a black box problem. So we have a blast exposure coming in, and we don't know what happened inside the brain because the skull is opaque, so we cannot see inside, and we cannot even measure the deformations. And second is there's a timescale barrier that in the head there's a two wave speed that share the same platform here. So we have the primary wave, which is determined by the bulk module of the tissue. So basically, it's coming from the bulk module of the water. So it's very fast. It travels around 1.5 kilometer per second. So basically, you think of this as a bullet going through. And then there's a shear wave from the brain tissue, which is very slow because the low shear modulus. You can think of the speed as me waving the hand. Okay, so there's two different time scale we need to capture when the blast hit the brain. The primary way, we're fast. We need something high speed to capture it, and we need something take longer time to capture the shear wave speed propagations. Okay. So the third one is the material complexity. So we know that brain is ultra soft and viscoelastic and heterogeneous. So it's very difficult to have a good phantom for the brain to understand it. Okay, so what's our solution for this challenge? We're just gonna make a horse as a sphere and innovate. Okay, that's what typical people use in solid mechanics. So first we're gonna open up the skull. We 3D print a phantom, skull phantom with a similar modulus as human skull cortical bone. And then we have a clearing protocol to clearing the skull. And now you can see that after our protocol, you can see the skull become very clear. You can even see the letter in the newspaper here. And the second part is we're gonna have embedded speckle pattern inside the gelatin. So we're going to use gelatin as our brain phantom, tissue phantom. And then we're gonna have two different camera to capture different speed. Okay, so thanks to the innovations from Jin Yang and Alex McGee in our group before that, we'll be able to have this technique to embed the speckle pattern into the gel. And the third one is we're going to use gelatin, as I say, to mimic. It has been shown it's a quite good surrogate for the brain tissue. So now we have the phantom ready to show the deformation in the brain. Okay, so now what we're gonna do is we're gonna have this phantom inside an advanced blast simulator. So we collaborate with Dr. Sarah Bento in Iowa State University. So what you're looking at here is the advanced blast simulator. So we have a driver section in the simulator which basically has a gas denotations zoom, and then it's going to generate a shock wave through the transition section, become a plane wave, propagating into the text section. And then we're going to have our phantom sitting in the text section, and we have different pressure sensor to measure the blast wave, the pressure. Okay, so here's the setup, illustration of the setup here. So we have the transparent scalp ring phantom, and then we have two different kind of constraints. So this we can think of free, suspended, or no net case. And this one we have a kind of rubber net and torso constraint. This to understand the effect of boundary conditions on the deformation. And here's our two picture of our experimental setup in the simulator. Okay, so I would like to give you a small illustration of what are the time scale and the events happening in the experiment. So we have a shock, you can see here, propagate from the left to the right. And then for less than 1 millisecond, the shock would wrap around the sphere. So we have that event called shock transit. And then we're gonna have a positive phase for the pressure to load the sphere. And then that all happens within few milliseconds. And then we're gonna have a head rotation coming at a much longer period of time, and the shear deformations coming along with the head rotation. Okay, so I'm gonna show you the roadmap of how we're gonna capture all this and characterize the blast exposure here. So as I showed you before, that first we need a good characterization of the blast exposure because that's our loading condition. So we have the pressure sensor on the floor, and this would give us the overpressure over time. And you can see that it followed pretty well Freelander waveform decay. And this would give us, by calculating the speed between these different the time between different signal rise, we can calculate the Mach number of the shock, and we can calculate the blast overpressure. Okay, then as I mentioned before, that we need two camera to capture two different timescale. One is the very fast shock transit timescale. So we use a Shimazu camera with 200,000 frames per second, and then we have a phantom camera which capture a much longer period of time to capture the head kinematics and the shear deformation. So first, I'm going to show you the result from this region, the shock transit regions and the pressure dynamics here. Okay, so here is the video, high speed camera video that from the Shimazu, and you can see that we use a digital image correlations algorithm to analyze the video, and you can see there's a clear banded regions, highlighted banded regions in the video. So the question we try to understand here is whether these deformations, apparent deformations, it's coming from the true deformations of the material, or it's just the distortion of the air coming from the shock. Because we know when the shock passes by, it's going to compress the air, and that will have a distortion to change the index of reflection. So that could appear as a deformation. So what we do is we track the velocity of the front. Okay, so this apparent front, we track the front and compare to the pressure wave speed in the gel. So if this is a true material deformation, it should have the wave speed inside the gel. However, we look at here, the gel has much higher wave speed than the shock from propagating here. So we believe that this is not coming from the material deformation. And also because we know that gel is hydrated gel or hydrogel or gelatin is mostly water, so it's almost incompressible. So volumetric loading or pressure loading, it's going to generate very little volumetric deformations here. So we can conclude that there's no observable deformations happen within the 1.2 millisecond, very early shock-brain interactions. Okay, so how about the cavitation I mentioned about, and what about the pressure dynamics here? So what we do is we synchronize our video with a pressure tape. So we have a pressure tape at the back of the head, just as other study have done, and we synchronize them together with the pressure with the video. And you can see that when at 0.5, it's where the maximum negative pressure happened. It's right after the shock wrap around, passed by the phantom, and you can see the magnitude is pretty low. So we plot out all the maximum negative pressure in our experiment, and you can see that most of them fell below the presumable cavitation threshold, and we didn't see any cavitation in our experiment. So we can conclude that there's no cavitations in the blast exposure here. So the takeaway for the very early shock-brain interaction is there's no cavitations and no deformation. So what happened then? Does that mean the brain doesn't get injured? No, we have to look into later time point, as I mentioned earlier. So then we're going to focus on structural response of the head kinematics and the shear deformation. So here's the video from another camera, from the phantom camera, with lower frame rate, but it record much longer period of time. I think when I play the video, you're gonna know what caused the deformations. So when you see the shot pass by, you see the gel start rotating and deforming inside. So we use a digital image correlations again on this video, and we can quantify the displacement field inside. And you can see that the internal deformations is predominantly circumferential. It's driven by the scalp rotations from asymmetry of the pressure. And you can see that when the scalp rotate, the deformations start building up from the outside, propagating to inside. So we know that now the mechanism of blast induced deformation is coming from the scalp rotations. Okay, so now we have the displacement field. How about the strain? Let's take a look at the strain field here. So you can see here's the video for the shear strain. You can see very similar pattern that the strain is coming from outside, propagating to inside. So if we try to quantify the spatial temporal evolution of the strain, I just plot a line here along this line, and you can see how the strain propagating from outside to inside. And we can get the magnitude from this plot. So it's in between around minus 10% to 20%. And if we fit the peak of if we get the arrival time of the shear wave and the radial positions of the location, we can fit the shear wave speed, which is around 3 meters per second. So which it's also very consistent with what people have been observed in the brain, human brain. Okay, so now we know that for the shear deformation, it's mainly coming from rotations, okay, from outside to inside. And now that we know that the shear deformation coming from the scalp rotation, that brings us another question. What also detect the scalp kinematic or the head kinematic? It's the boundary condition. So we can look into the boundary condition to see what effect does the boundary condition have in the deformations. I call it neck effect here. So what you're looking at here is the case that it's hanging, the sphere is hanging in the air, and we're gonna compare with our neck and torso constraint. So you're looking at here that it's a free basic spinning and rotations. And now I want you to look at the video of the neck and torso and pay attention to the neck at the bottom to see how fast it reverses, okay? So you see when the blast propagate from the left and hit it, it start going counterclockwise, and then there's a rapid reversal. So the head kinematic is very much altered by the constraint here. So if you're looking at how it affects the strain inside, so we have two locations, basic similar locations in two different boundary conditions. So we're looking at the red curve here first. So red curve is the shear strain from the no neck case. So this is hanging no neck case. And you can see it start clockwise because of the asymmetry of the pressure. So it start rotate clockwise, that give us a negative shear strain. And then it slowly reverse as the cable caught the sphere. But the reversal is very slow. You see it took around 25 milliseconds to reverse. But if you look at the blue curve here, it's the shear strain in the neck and torso case. You can see it start counterclockwise because now we flip the geometry and the asymmetry change. So it go counterclockwise at the beginning. And then you saw a very rapid reversal here coming from the constraint. Okay, so when we have a neck constraint, there's a rapid reversal in the strain. And what does this reversal bring us? It's the increase of the strain rate. So if we have a hanging case, you see the strain rate is around minus 20. And then if you reverse it, have a constraint, that would give us minus 60. So this tells us the rapid reversal from the scalp motion would increase the shear strain rate in the tissue. Okay, so let me just give a quick summary of our key finding here. So the key finding I want you to take away is that we have the blast exposure that would connect the head kinematics because of the symmetry in the asymmetry pressure field. So we can see that from the correlations here that we have peak angular acceleration scaled linearly with the peak overpressure. And this would give us somewhere around 30,000 rates per second square. And however, even though there's a very high angular acceleration, the angular velocity is not too high because the impulse time is pretty short. Okay, so what I'm trying to point out here is that the kinematic is coming from it's a key indicator for the shear deformations here. And then we can also correlate the maximum principal strain as a function of peak over pressure. And you can see that they also scale pretty linear. And you can see that at the BOP around 16 psi, this will give us strain around 50%. So it's pretty endurous. Okay, so the blast exposure can introduce quite a bit of head accelerations, and then that would give rise pretty high shear strain. Okay, as I mentioned before, that we also want to look into the shear strain rate because in people, the student in our lab have found that for higher strain rate, mostly higher than 200 strain per second, we don't see tau hyperphosphorylation. So basically, we don't see the possible. We kind of say we're not expecting the pathology of CTE when the strain rate is high, and we do see in our cell culture and tissue culture when the strain rate is below 200 strain per second, we do see tau hyperphosphorylation. So the strain rate, it's a indicate or like a kind of say it's an indicator of the pathology, how it translates. Okay, so if we have a higher strain rate, a higher BOP, we'll be able to see probably most of the time no CTE case because the strain rate is high. And for lower BOP and different constraint, we're gonna have lower strain rate, which is possibly to have tau hyperphosphorylations in the brain tissue that could lead to CTE case. Okay, I also want to show you that so most of our study blast over pressure range, it's coming within the tier 1 weapon system. Okay, so this is the key summary, but I also want to just how am I doing on time? Am I still good at time?
Oh,
Okay.
you're good.
Yes, you're
Yeah,
still
you're good.
Okay, so I just want to just touch a little bit about some of the numerical or theoretical work that we've been trying to develop to predict the deformations in the experiment. So I want to give you guys a brief overview of in detail of what's the physical mechanism behind it here. So basically, this is a shock solid interaction problem. So what you're looking at here, that it's an illustration of what happened in the experiment, right? So we have the shock from propagating from the left to the right. So this is ambient conditions, and we have a post-shock condition. Basically, the pressure is going to rise to the incident pressure, and then when the shock hit it, it's going to have some reflective pressure on the phantom that's going to load the phantom, and then we have two pressure sensors here. Basically, what I try to do is to use these two pressure measurement to see if I can build up a numerical framework to predict what's the deformations inside the phantom and compare against the experiment. So what we do is that we separate the shock transit into three different regimes. So the first one is what normally people refer to leak region. So when the shock hit to the front of the phantom, so it's gonna increase the blast over pressure due to the reflection. So we can use the reflection pressure from here to assign on the surface here. And then we're gonna have a wake regime. So when the shock just passed the sphere, past the equator, and it's gonna wrap around. So we're gonna have a wake regime, which is gonna have us slightly lower overpressure compared to the incident pressure. And then we're gonna have an attachment at the very end when the shock just passed by. So what I did here is to fit the pressure at different surface orientations. So mu here you're looking at, because the reflection is changing with the orientation of the sphere. So we can fit it from the CFD and simulation. And then basically from this, we can get the pressure distributions on the sphere at different time point. So basically we get the pressure on the sphere over time by splitting them into three different regimes. And with this calculation, we can we'll be able to get the net moment for the phantom and the impulse and the net force. So basically, once we have the net moment and the net force, we're just gonna I'm just gonna use the finite element simulation to predict what's the head kinematic. So what I did is we have a Scout gel model and we use the moment calculate from the flow structure interaction there, and then you can see. Let me see if I can play the video here. So if we plug in the moment and the force, you're gonna see the Scout star rotate, and we compare the angular displacement versus our experiment. They match pretty well here. So basically, we'll be able to extract the net moment and net force just from the pressure sensor reading in our experiment. So this is pretty good. And then if we have this rotation, what happens is the rotation is going to drive the deformation inside the brain because they are bonded together, right? So here's one of the way to show the shear string, maximum principal string inside the phantom if we have the net moment applied to the model, which is pretty similar to what we have on the shear deformation from the experiment. So I think for now we are getting a step that pretty confident that we have some predictive capability to reproduce our experiment, but we still need to consider like the boundary condition and all this thing. But this is just to give you guys a brief overview of how does the pressure from the blast exposure can convert to the net moment. And then the net moment will lead to the head rotation, and the head rotation will drive the shear deformation. Okay, so the conclusion here is that the dominant deformation mechanism is not cavitation, but the shear wave propagating from the rapid rotation of the head due to the net moment from the pressure loading. And this is important because this is the same mechanism as most impact TBI. And that's why at the beginning I showed you the similarity between the pathology from conventional TBI and blast TBI. It's because they all driven by the shear wave propagations from the head rotation. Okay, so this is important. And of course, we can correlate the BOP versus head kinematic, especially head accelerations and no cavitations. And then, of course, the neck torso constraint, as I show you, will amplify the strain rate, but not the peak strain. Okay, so I hope that our study can provide a direct and quantifiable blast to injury deformation pathway that will help us to better define the biosafety limit for the warfighter. Okay, so here is my question site, and thanks everyone for listening. I'm happy to take questions.
Thank you so much, Dr. Chen. It was a great, very detailed talk. Are there any questions from the audience? Okay, if not, I'll just get it started. Do you expect the dominant deformation mechanism to vary with head size, geometry, or material properties?
Yeah, I think that's very good questions, and I think it's an important question that now we use this head phantom, right? People will ask, how does this thing change for a real human head? Okay, so the answer for that is it's all come down to the net moment and the asymmetry of the pressure field. So I want to show you here that imagine if we have a sphere without the head or without the neck on the bottom, on the top. What happens is when the pressure just hit it, the sphere is just gonna translate. So there's not gonna be rotation because there's no moment. So the head geometry will all come down to the asymmetry in the head geometry. So if you have higher asymmetry geometry, that would possibly to convert more pressure to the moment, and that would be more dangerous. But if the opposite case, you have more symmetry in the head geometry, that could be the other case. But it all comes down to the asymmetry of the geometry.
Thank you so much. I think Sean raised a hand first, so maybe you can go ahead.
Oh, thank you, Otki. Thank you, Enze, for this great presentation. Amazing work. I have some questions about the content you showed in slide 19. Yeah, I believe you use the net a net moment plus a net force uh, to equate the boundary conditions from the shock. Is that the
Yeah.
case? Yeah.
Yes. Yeah.
I wonder how, yeah, I think in general this makes sense, but I wonder how that can replicate kind of like the local damage we have, for example, or maybe the local pressure or local deformation we have, on the front side of the phantom, under the pressure of the, blast.
Yeah, that's a good question because at the beginning we don't know if there's any is if there's going to be any scalp fracture or deformations on this on the Phantom. But because from the high speed video that we took, we look into it. There's very little deformations because the gel inside is pretty incompressible. So any pressure try to squeeze the gel will not be able to deform it. So we believe that the local damage does not really play a role here to govern the shear deformations. The main deformation is coming from the kinematic, the rotation. So that's why the equivalent to just use net moment and net force will be enough because it's all a system of motions here. It's not we don't really need to worry too much about the localized deformations on the scalp.
Yeah, I see. I have a follow-up question about the
Mm.
phantom configuration. So I guess in your simulation work, you treat it as an incompressible hyperelastic material, or you just yeah, how did you
Yeah, we
impose the
just use a incompressible material.
I
Like
see.
basically we just need to have a very high bulk modulus versus the shear modulus. That's enough. I think it has to be five 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 orders, magnitudes different, 4 to 5 orders difference. That would be enough.
I see. Well, thank you. Thank you so much for for answering those questions.
Bijun, you can go next.
All right, thank you, Audrey, and thank you, Enze, for the very interesting talk. I have two quick questions. One is from your experiments, other one is about your FEM simulation, but I can go with the experiment first. So you are talking about your skull with some hydrogel inside, right? And
Yes.
looking at high-speed videos, one thing that immediately comes into my mind is the kind of material property of your gel, like how viscous your gel is, right? Like is your modulus and your hydrogel viscosity similar to what your human brain like have inside?
Yeah,
Or
that's a good
yeah,
question. So I think we get asked this question a lot. So there are two parts. One is the shear modulus, one is the viscosity part.
right,
So we believe for the shear modulus is pretty close because we can measure we can measure here we can measure the shear wave speed, which is similar range of the brain. Maybe brain is a little bit softer. So in terms of the shear modulus, yes. But for the viscosity part, so the gelatin is pretty there's not much viscosity inside. It's pretty like we could think of as a new hooking material. So there's not much viscosity inside. So at that part, we still need a better, maybe better phantom gel, brain phantom if we try to capture the viscosity part of the brain here. So
okay,
because you're looking at here that so if it's very viscosity, I think there's gonna be some damping of the deformation that would die
right,
out very
right,
soon. So in gelatin, probably not. So you will see this energy kind of get trapped inside the gel and start oscillating. So so that's a really good question. I think we also would think about maybe in our next round of experiment, we can add some different ingredients into the gel to make it more viscosity.
right, right. Or you can even do something in your finite simulation to study effect of, viscosity or something similar. Uh,
Yes, yes.
on your, I think it's gonna definitely affect your head kinetics because intuitively, if the gel is more viscous, then I guess it's rotating slower, giving the same blast pressure.
Yeah, so
Right.
to answer that questions, I think you have a very good instant here that so you should we can think of this as a energy perspective. So if you have a blast coming to hit the phantom or the head, it carries certain momentum or energy, right? So it all goes down if all the energy, there's no damping, all the energy would go into deformation. So if a viscosity part, that would actually maybe reduce the deformations and the rotation because the energy can go somewhere to damp out rather than just stay inside in the system here.
Mm-hmm. And yeah, following up on that question, I think my second one is about because it's high strain rate deformation, right? So there may be some local heat that you may have to consider when you analyze your results or you're considering in your dynamic simulation. And another one is about in your dynamic simulation. I'm assuming you are not doing sort of viscoelastic model.
No, we don't because we use gelatin here. We believe it's pretty for new hooking model would be sufficient here. What we're
It's
looking at.
Because I remember you have one slide that you show something about viscoelastic properties at high rate or something like that. And I was just wondering, would you be interested to consider those kind of material property complexity into your dynamics
Yeah,
model or future?
that's a very good point. So I think in here that no, we have somewhere here. Yeah,
Right.
so actually for this case, we have a student in our lab who characterized the property at super high rate. So this would be 10 to the 3 and 10 to the 6. But for our case, we only see somewhere in sub hundreds. So we still believe that for this range, the characterization from here might not need it for our case, but that's a good point. It does vary with the string rate here, the the property, especially the viscoelasticity for the real brain tissue. So
Right. And I guess temperature may be also a control factor as well, especially if you're in a high rate. But yeah, that's pretty much
yeah,
what I want to
yeah.
ask. Thank you.
Um, so maybe we can shift the gears a little bit. I want to ask you about your experience in medicine. How would you compare research and experience there
Do you want
compared to Johns Hopkins University?
me? I think you mean in general research environments. I think here it's a little bit like a bigger university, and I'm lucky to work in this under this Panther program. So I have a lot of opportunity to collaborate with different people, and it's very nice that I have the chance to collaborate with people from different backgrounds and different universities. So that's a big difference when I compared to when I was in Hopkins. I was pretty doing most of my research within our group, but here I get chance to collaborate with more people, and that opened up my perspective a lot. Yeah.
What has your experience been like transitioning from traditional solid mechanics to the mechanical analysis of a brain tissue?
Yeah, so I think for me it's not super challenge because my advisor he has pretty similar background in mechanics, so he's a mechanician. So that helps that we still be very serious about mechanics rather than okay, if we do something just focus on biology, maybe we're gonna be less rigorous on the mechanics. So that helps that I think that still we still both have a strong interest in solving the mechanics right, then we talk about the biology. So that's important. But the challenge, of course, that I think in mechanics where lots of things it's pretty control and ideal, right? So you do have lots of assumptions and control for things which you don't have when you're dealing with real biology. You just have to find a way around it to still make your assumptions in you need to make it work in the biological system, but you don't want to lose the rigorous analysis in mechanics. So that's a kind of trade-off. But I think I'm lucky to have my advisor to kind of like mentoring me in that perspective. So yeah, so if anyone wants to do it, I think it's a great combination. There's so many problem can be solved by putting mechanics and biology together. So
Yeah, it sounds great. And lastly, what advice would you give to current or prospective graduate students interested in mechanics?
I think my thought is this, as I mentioned, that you should always take it serious. That sometimes when you switch gear to like different application, the fundamental still going to be the same. If you're looking at the problem I solved today, right? It could be a brain, could be other things, but the fundamentals still coming from, the wave equations and how does the energy convert from, from external loading to uh, internal string energy and all the things. So I think if you get a good foundations on mechanics, the principle, you'll be able to open up and apply to a variety of different application. It doesn't really constrain you from doing what you have. So I think just go back to the fundamental, but and kind of like if you can think of the problem and draw a free body diagram out of it, everything could be solved. So that's what Christian told me too. Like when you take a problem, it could be a very complex system with lots of components, biology inside. But if you can draw a free body diagram and write down the governing equations, then you'll be able to at least a good understanding of the physical mechanism behind it. Then you can talk about biology and all this stuff. So
I think that's a great idea. Yeah, it's a
if you
great.
just draw a free body diagram.
That's a great advice.
Yeah.
Well, thank you so much, Enze. It was a great talk, and thank you so much for the wonderful discussion. We're going to be following your future work.
Yeah.
And thank you, everyone, for joining our seminar today. And we will see you again soon.
Yeah. Bye bye.
Bye.